All right, everyone, we are on our second problem for our exam two. So we're told a lot of things here. We have our fundamental equation, eta, right here. Oops, it's responding. Give it some time. There we go. So this is our fundamental equation. It's a function of these parameters here. So let's go ahead. We're told blah, 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 relative varies from 0 to 1. 0 would indicate no binding. 1 very strong. The experimental edge is this. The conversions from micrometers is 1 to 1. To measure the size of my magnetic particles, so I have a resolution. So let's kind of back up here. So we have our function eta, which is delta x over pi r, actually 2 pi r, 2 pi r omega tau. So when we look at this side of the screen, pixels to micrometers 1 to 1, I can resolve up to 0.1 pixels. I use a DAC that sends magnetic field coils, and it has a resolution of 1 nanosecond. When measuring the frequency of magnetic field, I'm only resolution 10% of any given frequency measurement due to some induction effect. I measure displacement of a particle 17 times, so I have n particle equals 17. Mean displacement, number of del x. My x bar del x is found a mean displacement of 100 micrometers. 100 times 10 to the minus 6. My standard deviation of delta x is equal to 2 times 10 to the minus 6. We also have basically an uncertainty of delta x, which is going to be equal to 0.1 times 10 to the minus 6. We have an uncertainty in the time, tau, which is going to be equal to 1 times 10 to the minus 9, and an uncertainty in frequencies, which is going to be equal to 0.1, because it's 10% of any given frequency measurement. Excellent. Nominally, the diameter, so x bar of d, so x bar of my radius should be equal to 4.5 times 10 to the minus 6. We're not given any information about that measurement here in r. The actual tau, so number of tau is equal to 98. My tau, x bar tau is equal to 5. My s of tau is equal to 1 times 10 to the minus 6. Calculate the uncertainty. All right, we got a lot going on here. So let's break it down. We have delta x, we have r, omega, and tau. So boom, 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 boom. Bias, precision. So we do have precision in delta x because we have a number of measurements. We have precision in tau. But we don't have any other precision measurements because we don't have any other numbers. So boom, boom. Do we have bias in delta x? Yes, because we have an uncertainty there. Do we have a bias in tau? Yes, we do. Anything else? Ooh, tricky one here. So we're using this screen, so actually we have an uncertainty in r, which is also going to be equal to the uncertainty in delta x. Oof, tricky. So yes, there is a bias there. And then for our frequency, do we have any uncertainty there for the time? Yes, there is uncertainty frequency. So we have bias everywhere. All right, so let's start to break this down. I'm going to pull up a Mathematica notebook. We're going to actually do a new one. New. Let's get this one. I'm going to quit the kernel. And then I'm going to zoom in here because I want to... For me, I wanted to write down some of these values so I can kind of visualize everything. So I'm going to call this my rolling RP is equal to del x divided by 2 times pi times r times w times tau. So those are my function. We're going to say that n del x is equal to 17. X bar del x is equal to 100 times 10 to the minus 6. My s del x is equal to, what's going on here? Shift enter. S del x is equal to 2 times 10 to the minus 6. My uncertainty in del x is equal to 0.1 times 10 to the minus 6, which is equal to the uncertainty in r, which is equal to u del x. Because I'm measuring, again, basically measuring it on my screen, the radius of those particles. So we have to measure that as well. Uncertainty in omega is equal to 0.1. Our uncertainty in tau is equal to 1 times 10 to the minus 9. And an s of tau is equal to 1 times 10 to the minus 6. My x of r, my x bar r is equal to 4.5 times 10 to the minus 6. The number of tau is equal to 98. My x bar tau is equal to 5. My s tau is equal to 1 times 10 to the minus 6. Equals 1 times 10 to the minus 6. All right. So we know, I'm going to just move this over. If we have precision in x, so my precision would be my, and actually, let's go ahead. So we know that for delta x, I need my t of 0.005 of 16 and t of 0.005 of infinity. So let's go over here. So t of 0.005 of, what was it, 16? Let's check it. Yep, 16. So t, I'm just going to do this. T 005 nu of 16. Sorry, I'm just moving this around so we can. 16 should be what? T 005, 16, 2.921. Good. And then to infinity, 2.576, 2.576, 2.576, 2.576. T005 nu inf equals that. All right, so let's go ahead and let's get back to where we're at. Nope, you stay there. You go right here. Now let's pull it up again. All right, so for my precision here, I'm going to have T of 005 nu 16 times, actually, let's do P del x is going to be equal to T005 nu times 16 times our S del x divided by square root of nx, n del x. And then we're going to take this whole thing and divide by x bar del x. Good. We also have P of precision error P tau, which is going to be equal to T005 infinity times S tau divided by square root of n tau, and then all of this divided by x bar tau. Precision, bias, or now I need to do bias. So we have bias in everything, so I need to do drp d del x is equal to derivative of eta, or rp with respect to del x. Good. I'm going to do the same thing for here. So instead of del x, we're going to have dp dr with respect to r, drp dw equals derivative of rp with respect to w, and then finally we'll drop this dr p d tau is equal to derivative of rp with respect to tau. So our we're going to now do our bias. It's going to be equal to square root of. So we need to do drp d del x times u del x divided by rp, the equation, squared, plus, we're going to copy and paste this. So we need to do it 3 more times. 1, 2, 3. Good. So instead of del x, drp d capital R, u r rp, good. Now we're going to do drp dw uw omega over rp. And then we're going to do dr d tau drp d tau times u tau. And again, we're able to convert that uncertainty into a fraction, and it's completely fine because, again, we're converting everything into fractions as well. So we can work with that value. Alternatively, you can potentially calculate like the nominal value of, what frequency is, which I believe we were told that, let's see here. Where is our nominal value? I'm measuring the frequency of my magnetic field. Told this. Values from 0 to 1. Let's see here. Frequency. Found a mean. Standard deviation. But we could actually leave that out, and we'll go ahead. Let's go ahead and see what we got here. But again, we could use that as a fraction. So, got my bias. Actually, we do need, but we should be told in here, and there may be a typo, but there should be time resolution. There should be a typo that our omega should be 1, basically. Yeah, there should be a typo where our nominal omega is basically 1 hertz. So we'll plug that in as a value, but you could just replace it by 0.1 too if you would want to. So let's go ahead and do that. So slash dot, we're going to do del x goes to x bar del x. We're going to say that r goes to x bar r. We're going to say that tau goes to x bar tau, and then finally w goes to 1. So that's going to be our bias. So our total is going to be uncertainty, and RP is going to be equal to square root of precision P, where is it? P del x squared plus P tau squared plus bias squared. And there we go. Dominated by bias for sure. So how could we improve? There's a couple. I mean, we have fairly good, I'd say a nanometer resolution is very good. If we were better in frequency, so if our UW is better, I think that would be our big factor there. So there you go. That is your problem 2 done. So we'll see you in the next video. Thanks. Bye.